So today, welcome everyone back to the Asia Pacific Analysis and PD seminar. Unfortunately, Professor Ki-Ahm Lee is currently on travel to the United States. So he asked me shortly before that I replace him today to chair this session. And Woongbae is, do I pronounce your name correctly?
Yes, that's good. Woongbae, yes.
So he's currently a postdoc of the University of Pittsburgh in the United States. And he did his PhD at Michigan State University.
Yes.
And, today he will speak about his research, coupled geometric flows with harmonic map flow. So Woongbae, please start.
Thank you very much. And thank you for having me in this wonderful seminar. The COVID situation make it very hard to attend the seminars worldwide, but this kind of remote seminar make it possible, especially for the Asian Pacific seminar. Looks very wonderful. I mean, we have both in summer and in winter at the same time. Good to see people in different weather at the same time. It's my pleasure to be here. And I'd like to talk about the coupled geometric flows with harmonic map flow. So the outline of the talk is the following. First, I introduce the heat flow of the harmonic map, the basic kind of building model and its properties. And it enjoys the smoothness, regularity only under specific situations. We don't have all-time smoothness, but only kind of partial regularity. So, well, it's not from this point of view, but kind of explanation could be possible that people try to think it's combination with others, especially for the evolution equation for the metric. So I will introduce three of them, or there could be more, but they are high-cumular flow of harmonic maps, conformal heat flow of harmonic maps, and harmonic ridge flow. So my first topic is the harmonic maps. So let M and N are Riemannian manifolds. The directional energy of a map is defined by the following. Energy is integral of little e of f, which is the energy density defined by df squared times the volume form, 1/2 of. And it is written in terms of both the metric in the domain and metric of the target. So G is the metric of the domain, H is the metric of the target manifold. And harmonic map is a closed, the critical point of the directional energy. And in general, it is weakly harmonic map. And if it has more property, then we have different kind of in front of the harmonic map. Okay, and in equation point of view, if we embed the target manifold into the Euclidean space isometrically, then harmonic means the map F, now it is a vector valued function. It satisfies the following equation, tau of F equal to 0, where tau is the tension field of the map, which can be written as the Laplacian plus second fundamental form A. So in PD point of view, it is a system of, because it's vector valued, system of semi-linear elliptic equation with non-linearity to be square of df, or df square. Because in second fundamental form, it's growing like square sense. All right, so this is harmonic map equation. And it's pretty much similar to the harmonic functions, and actually can be viewed as a generalization of harmonic functions, but it has somehow a different behavior than harmonic functions because of the system and because of this increasing feature for the second fundamental form. So those are few known results of the harmonic maps. Of course, there are more, but due to the time and due to the space, I can only pick several of them. So let F be a map and let little m to be the dimension of the domain. Then digital energy is conformally invariant for two-dimensional domain. And this two-dimension is also very important in regularity sense. Later, I will explain it. So it is somehow called critical dimension of harmonic map. And in two dimension, we have the following quantity, so-called Hopf differential. In isothermal coordinate or in complex coordinate, it is written as this way: fx squared plus f minus fy squared plus twice of I times the inner product between f of x and f of y times dz squared. So this Hopf differential is holomorphic. This quantity is also important that you can use it to estimate the, for example, the energy of the harmonic map, its difference between the critical point and nearby point, and so on. So it is widely used concept. And in terms of irregularity, again, two dimension is critical dimension. So people are not aware of the smoothness of the harmonic map in two dimension. So far, people only knew that continuous harmonic map is smooth in two dimension until Allen showed that any harmonic map, weakly harmonic map, is smooth in two dimension. By the way, one-dimensional harmonic map is geodesic, exactly the geodesic equation. So it is simply smooth. And we know that now two-dimensional harmonic map is smooth. On the other hand, higher dimensional harmonic map is not smooth in general. And an example made by Rivera showed that a harmonic map from three-dimensional ball to two-dimensional sphere could be discontinuous everywhere. So it's pretty bad regularity. So people try to understand now the dimension of singular set. And there are two very well-known facts about dimension of the singular set. In general, it is n most n-2 by Xuan. But if harmonic map has additional property like minimizing harmonic map, then its dimension of the singular set is n most n-3. So in particular, from three-dimensional minimizing harmonic map, it could have a point discontinuity. So that's the property of the harmonic map, pretty wild. But if we consider a heat flow of harmonic map, things are again slightly different. So heat flow is simply f sub t equals to the tau of f with initial condition. So in terms of harmonic function and heat equation, of course, both are smooth, but probably the smoothing effect of the heat equation, I guess similar thing happened here. So even if harmonic map itself may not be smooth in higher dimension, but heat flow is smooth, at least short time. That's a very critical result. by Ears and Sampson, 1964. For any smooth initial condition, there is a T naught such that heat flow admits a unique smooth solution. Moreover, if we have additional condition on the target, curvature assumption on the target is given by non-positive, then we get global smooth solution as well. And this fact is basically come from the Buckner's technique. So compute the applying of the energy density and use the change of the derivatives, we get curvature condition. And for non-positive curvature, we have the desired sign and get the return. Okay, so people wonder what happens for positive curvature case or simply without any curvature assumption. Then in 1985, Struve showed that in two-dimensional case, we have global weak solution. So for any initial map in W12, there exists a solution smooth except finitely many singular points. These are similar to the singularity from sequence of harmonic maps, and the terminology bubbles also come from the famous paper of Sachs and Uhlenbeck. But Struve also shows similar result in heat flow as well. And the description of the singular point is that the limit of the energy over small bore, we first take time to be the singular time and shrink the radius. Then it's kind of a point energy. So over the regular region, it should be 0. When taking R to be 0, the energy should be 0 near the regular point. But at the singular point, it's non-zero. Later, I show you the picture, but it describes kind of the energy concentration at the point. So we call that point to be bubble point. And the amount of the energy concentrated at the bubble point can be captured by so-called bubbles, which is defined by the map from sphere to the target manifold. And it is constructed in the sense that we choose the energy, the map over here from the bore near the singular point, and it conformally change the domain to be the large disk, larger and larger disk, and take the stereographic projection to make the domain to be the sphere. That's how we construct a bubble. And the following energy identity hold. So the whole energy of the map F can be captured by the limit energy plus the bubble energy. And because bubble energy should have some non-zero lower bound, so if the initial energy is smaller than that lower bound, then bubble cannot form. So the solution is smooth globally. That's kind of corollary. Okay, so we know these facts. And one very interesting description for the bubble is this picture. So the upper picture shows you how the energy density, the function on the domain manifold, evolve, like concentrating at this singular point where we choose some bore of radius r, so that the energy over this bore at singular time should be non-zero, whatever radius you choose. And the below picture shows how we perform a conformal change of the domain to make the bubble map here. Phi sub I is a bubble map. So we choose this tiny bore and expand it by conformally changing it. And after stratigraphic projection, it covers almost all the spheres. At the limit, it covers all the spheres, so we build a bubble. While this annulus region maps to the region connecting the bubble and the body map. So it is called the neck. And it's also a topic that whether the neck actually exists or what's the energy that the neck contains or the diameter of the neck and so on. So those are so-called neck analysis. But I skip that part here. Okay, so after Struve's work, people wonder whether the finite time singularity actually exists, and it is. So in 1992, Chang-Ding Ye construct an example from disk to the sphere such that the solution blows up in finite time. And using this argument, later, Davila del Pino Wei in 2020 constructed an example such that whatever points on the domain is given, they construct a solution that blows up exactly at those points. So that's general result. And one property of the bubble is that two bubbles should decoupled in the sense of Quantian. That means two bubble points, of course, could be different space or different time. But if they have the same location and the same time, their kind of concentrating speed are so different so that they are formed in distinguished sense. So their, for example, energy should not be mixed up together, decoupled. Okay, one more thing. There is a uniqueness property and energy decreasing property, and harmonic heat flow enjoyed energy decreasing done by Struve, but his sense is that the derivative of the energy, time derivative, is non-positive, or almost every t if the solution is not smooth. So in 1995, Freire showed that if furthermore the energy satisfied this kind of comparison property, E sub s is less than E sub t for almost every pair s less than t, then the weak solution is unique. But there could be a possibility that the derivative is non-positive for almost every t, but not strictly enjoy the comparison property. So Struve's solution allows bubbling off, of course, but it also allows, theoretically, so-called reverse bubbling. So bubble travels outside of the solution, and suddenly it hit our solution and join to the solution. So that's called reverse bubbling. It's not bubbling off, but bubbles kind of bubble on. And in 2002, Topping actually constructed a solution having the reverse bubbling. So that's the description. So it is a constant map for the time from 0 to 1, but so we expect that it should be constant forever, but it's not. At time 1, something happens. Bubble touches the solution, attach it, then it deserves like the reverse of the bubbling process. So when we take the limit of the energy from t from the right, so from the future past, then the energy limit is the initial energy plus 4 pi. So this 4 pi is the amount of the bubble energy attached at the time t1. All right, so that's heat flow of harmonic maps. So smooth, but finitely many exceptions, so-called bubbles, and bubble do exist, and it enjoy such interesting behaviors. Okay. Now I'd like to discuss about technical flow, the extension of the heat flow of harmonic maps coupled with the metric. I first described the decomposition of the metric in 2 dimensions. So roughly speaking, the space of the metric is decomposed by 3 different directions. The tangent space of the metric decomposed by 3 different directions. One is conformal direction. Another is Lie derivative direction. So it's done by pullback of the diffeomorphisms of domain. And the last one is so-called horizontal direction. For me, it's unclear what the meaning of this space, but it is called horizontal direction and consists of real parts of holomorphic quadratic differentials. Okay. But essentially, if we evolve the metric, the direction of evolution should be within these 3 possibilities, or maybe combination of them. Conformal direction, pullback of the diffeomorphism direction, and so-called horizontal direction. And 2-dimensional domain, we already know that conformal change of the metric doesn't change the energy. So Roughlin and Topping consider in 2016 the following concept. So if we choose a diffeomorphism in appropriate sense, then we can adjust the time derivative of the metric to be only horizontal direction. So they define so-called technical flow, which is a pair of equations. First, the equation of the map, that's the same as the harmonic map, heat flow. So Ft is tau of F. And the evolution of the metric is done by the following. Here, phi is the Hopf differential that we mentioned before. And P is the projection to the horizontal direction. And it's important that this projection is L2 projection, L2 orthogonal projection, so that this whole pair of equations enjoy the gradient flow property. So the equation is obtained by L2 gradient flow of the energy, but viewed by the functional of both map and the metric. So we are allowed to kind of fluctuating the map part and the metric part. Then fluctuating of the map part give us the traditional heat flow of the harmonic map, but fluctuating of the metric give us exactly the technical flow. So in other sense, under the technical flow, the energy decreases in the fastest direction. So good. So far, it looks good. It looks reasonable. And because of that reason, it is preferable in some sense. But because technical flow changed the domain, so there could be another possibility of singularity. Another type of singularity may arise. That's so-called domain degeneration. So here is the picture of domain degeneration. You can see there is a surface and this closed geodesic gamma may collapse under the flow. And of course, the closed geodesic could be here or could be there. The feature of these 2 degeneration are different. One doesn't decrease the genus, but it increases the number of the component at one part to the other. On the other hand, for the second case, it doesn't detach the domain, but it decreases the degree. I mean, the genus. So how do we deal with these kind of additional difficulties? So those are properties of technical flow. Again, of course, there are more, but I have limited time and space, so I only pick some of them. So first of all, they show that weak solution exists. And if maximal singular time is finite, then lengths of closed geodesic should go to 0. In other words, the domain should degenerate at the singular time. And if the length of closed geodesic goes to 0 as t goes to infinity, then the domain should split into finitely many surfaces which has lower genus, and the map subconverts to branched minimal emergence. That's the result. Furthermore, the energy is not lost. Again, when degeneration happens, people wonder what's going on for the energy. And the energy of the main part are not bad, but the issue is the energy nearby the degenerating point. In the picture, like energy nearby this point, energy nearby this singular point. And they show that energy is not lost. And actually, if the target manifold has non-positive curvature, then similar to the usual heat flow, there is a global smooth solution. And finally, if the domain degeneration occurs at finite time, we get the same result. Okay, so that's the properties. And unlike the harmonic map heat flow, there can be necks connecting bubbles and body maps. In other words, in harmonic map heat flow, we already checked that energy is not lost, but furthermore, the diameter or length of the neck is 0 in there. But here, there could be non-zero lengths of the neck connecting the body and the domain, body and the bubbles. And this happens when domain degenerating, not when energy is concentrating. So good flow, but has its own difficulties and issues. All right. So people try to think different direction of changing metric to avoid this kind of difficulty. So for example, Ki-Ahm flow has an issue of another types of degeneration, another types of singularity, and that's due to the domain change. So one may think that, what if we evolve the metric in the sense that the geometry of the domain doesn't change? But that's, of course, conformal heat flow of harmonic maps. The idea is the following. Consider a variation of the metric that doesn't change the domain geometry. Especially if we force the metric only conformal direction, then the domain geometry doesn't change. So we let the metric to be e to the 2u times initial metric, and we consider where the df squared, the energy density, is large. We want the conformal factor u to be large as well. The following picture describes the idea. So here, time goes to the singular time. So energy density blows up, concentrating to the singular point. And this red circle indicates where the energy is large. But then under the conformal heat flow, this blue region is where energy density is large. So we want E to the 2U to be large. And this means that we kind of enlarge the domain. In the next picture, we have bigger circle in blue compared to the red. So they have the same amount of the energy because of the conformal invariance, but the domain itself is larger. That means the function value is smaller. So you see the black pop up and blue one, then blue one has smaller energy concentration. So in that way, we expect that this conformal heat flow may kind of delay the energy concentration. So it may delay the singularity formation. But it may, we don't know yet whether it actually do that or not. But the idea is that. So using that idea, we can consider the following parallel equations. So the map part is the same. It is a heat flow of harmonic map. And the metric evolution is only on the conformal direction. So G sub t is just a number times the same metric G. And the number is large when energy density is large. Number is small when energy density is small. And we put A and B to be some suitable constant, positive constant, to control the behavior of the flow. And we can let G to be E to the 2U times G naught, then the equation becomes the map, the same, and a function. Now U is just a scalar function, so it's easier to handle, and you enjoy this equation. Okay, so that's the conformal heat flow. We can consider the volume of this flow because the metric changes. We may consider the volume to be a time-dependent function, which is this way. And again, in two-dimensional domain, we have it's very quick and simple computation, the following lemmas. So energy is decreasing. Same reason for the heat flow. And volume seems like it's increasing because we put the large factor of the conformal factor whenever df square is large. So volume looks like it's increasing. And it may, but it doesn't go to the infinity. There is an upper bound of the volume, which is given by blah, blah, blah. And we can achieve it because of the constant A here. So that's about the volume. And about steady solution, if the map is harmonic, then F doesn't change. F is a now constant map in time independent. Then the equation for the matrix says that the energy density becomes a constant, the ratio between A and B. So the effect of the conformal heat flow whenever the map is initially harmonic is that it redistributing the energy density in the even sense. So suppose we have a high energy density, then we enlarge there to reduce the energy density. If there is some more energy density, we shrink it to increase the energy density instead. Okay, so that's the main result of conformal heat flow. So far, we know that there exists a short time so that the solution exists in smooth sense over the short time. And a global weak solution exists where singularity is at most finitely many. So similar to this true-best solution. And furthermore, at the singularity, the energy density should blow up. So unlike the technical flow, there's no domain degeneration. So only the energy concentration occurs at the single time. But it's still ongoing problem. So we have many questions that are not yet answered. Like, is it really avoid finite time singularity, or is the solution unique? Like, reverse bubbling happen, or is there infinite time singularity? There are many questions left yet. So it's also another variation of coupled geometric flow with harmonic. Okay, my final topic is harmonic rich flow. So that's a little bit different taste, because the main origin of this flow is from rich flow, not harmonic flow, but it enjoys similar perspective in the sense that it coupling the harmonic map flow and the evolution equation of the metric, and in the sense that it try to avoid the singularity of the map as well. So in the sense, it's also a variation of coupled geometric flow together with harmonic maps. So I put it here. Also, it arises very naturally from geometric context. I will say that. So let me introduce the harmonic rich flow. So let F0 to be an initial map and G be a time-dependent metric. And we consider a pair of equations. G sub t equals to -2 times Ricci plus 2 times some coupling function alpha and df product df. So that's the tensor product. And the evolution of the map is the same as harmonic map flow. Again, an example of this harmonic rich flow arises in very specific geometric context, which is warped product manifold. So let's consider the domain to be some manifold M1 times circle with warped product metric to be G equals to G1 plus the factor e to the 2 phi times d theta square. Then the rich flow of this product metric reduced to the following pair of equations. Equation for G1 is similar to the above, negative twice of the Ricci of the manifold M1 plus twice of d phi times d phi in tensor product. And phi is a function. Equation for phi is exactly the heat equation. And you can see it's a special case of the harmonic mapping flow whenever the target is just R, or in this case, S1 with flat metric. So the harmonic rich flow is kind of a generalization of this warped product metric. Okay, so in this direction, people consider the harmonic rich flow. But also in my point of view, it can be understood in the sense that imagine why we couldn't get the desired property in previous approaches. So for example, in conformal heat flow, we couldn't get the desired result, maybe because the equation of the conformal factor or equation of the metric only have the df squared term, but not the Laplacian term. So without Laplacian, we cannot get a proper regularity property. So maybe that's one reason. But look at here, we have g sub t equal to negative twice of the Ricci plus some factor. So this Ricci, well, of course, Ricci flow itself may develop a singularity, but this kind of Laplacian would help us to get better regularity property for the metric. That's one hope compared to the conformal heat flow. Okay, so let's see the actual results about harmonic heat flow. This mainly introduced by Mueller in 2012. The solution exists for a short time and is unique. He showed the unique short time existence. And in broad sense, the solution can be seen as a gradient flow in the following sense under some condition. So the coupling constant alpha, where it is positive initially, but furthermore assume it is non-increasing. And e to the negative of phi is new function. Suppose this function solves a joint heat equation. So it is heat equation, a joint sense with extra factor r minus alpha df squared. R is a scalar curvature. And yeah, others are very good. So suppose e to the negative phi solves this equation, then the following functional, he said it is from Perelman's functional, so similar to his functional, but this functional integral of the scalar curvature plus d phi square minus alpha times df square times e to the negative phi dv. This functional is non-decreasing. So it's called energy functional, but non-decreasing, so it's not non-increasing. So in the sense, our solution Fg is positive gradient flow, not negative gradient flow, so a little bit different. But it can be interpreted as a gradient flow for particular chosen phi. So the equation is again derived from gradient flow of certain energy functional. Okay, so how the flow behave near the singularity? They also show the following facts. First, if the coupling constant has strictly positive lower bound, and if capital T is a singular time in the sense that the density blows up, then the curvature also blows up as well. Here, the curvature is a scalar curvature. And later he showed the Riemannian curvature estimate in the following sense. Furthermore, suppose alpha has upper bound, finite upper bound, and let's say capital T to be maximal singular time, in the sense that df squared blows up, then the maximum of the Riemannian curvature tensor should be also blows up. So that's kind of description of singularity. So at the singularity, if df squared blows up, then the Riemannian curvature tensor should blows up as well. Okay, so far it doesn't say there exists smooth global solution. But one good thing for this harmonic rich flow is that it doesn't restrict the domain, the dimension of the domain. It can be arbitrarily n-dimensional domain. So if we restrict ourselves to two-dimensional case, of course, sometimes restriction lose some property, but sometimes restriction gain the properties, and in this case, the latter happens. So a special case of two-dimensional domain is the following. It's done by 2017, Buzzano and Roughlin. And Buzzano and Muller are the same person, I think. Changed the last name, but anyway. So now we focus on two-dimensional domain. Then furthermore, from the previous results, we get more properties. And the first one is that the solution and maximal singular time, capital T, is the same. Then both map and the curvature must blow up. So in the previous theorem, it says if the energy density blows up, then the curvature blows up. But this theorem says both must blow up. So there's no possibility that like curvature blows up, but map doesn't blow up. No way in two-dimensional. And of course, two-dimensional case, there is only essentially one curvature exists. That's either scalar curvature or Gauss curvature, as twice of one to the other. So essentially one curvature. So here, capital K is the Gaussian curvature. But both curvature and energy density should blow up. Therefore, the next line, if the coupling function satisfies the following conditions, so the lower bound is bigger than some threshold. Here, the case of tau is the sectional curvature of the target manifold in direction tau. So target manifold may be high-dimensional, so it has several choice of pair of planes, pair of directional vectors, so choice of planes. Then we can consider a sectional curvature of the target manifold in that plane. And maximum of them, twice of them, if alpha 0 is bigger than twice the maximum of that sectional curvature, then the solution exists and smooth for all time. The argument is the following. If alpha 0 satisfies this condition, then the energy density cannot blow up in finite time. Therefore, curvature also cannot blow up at finite time. Therefore, there's no singularity at finite time. So it's very amazing in the sense of the following remark. The individual flows, rich flow and harmonic map flow, may develop singularity, finite time singularity or whatever else, but its coupling behave better if the coupling function satisfies this simple strict lower bound. So that's some kind of amazing fact, and well, maybe expected, maybe unexpected, but very wonderful fact, and it makes this flow, harmonic rich flow, to be very well-behaved flow. And of course, there are more properties, more research is going on in this topic, but yeah, we will keep working on the geometric flows together with the harmonic map flow. Okay, that's all for my talk. Thanks very much.
Any questions by the audience, maybe by the attendees? Please raise your hand and I can give you access to talk. If not, I have one question to the harmonic heat flow. So you had in one of the slides of the property that the initial map F needs to be in W23, I think, from M to N. Is this type of regularity natural or for the initial data, or is this, yeah, just, no, before? Yes, here. Conformal heat flow, excuse me, conformal.
Okay, yes.
Is this type of regularity, okay, even, so I find this quite regular actually, but maybe some people not, but is this type of regularity on the initial condition actually natural, or could one expect that if the initial data is even smoother that you get then global weak solutions? Because there are global existence, but I don't see what are sufficient conditions implying this actually.
Yeah, so unlike other flows, this flow is pretty brand new, designed by myself, and I could derive the result under the condition of W32, where I initially planned to start from W12, but I need more regularity on the initial maps. That's why I changed it to W32. Maybe somebody else can derive the same result under weaker assumption W12, because W12 is more general, more natural, but just because I couldn't.
I see. Okay, so this is a technical condition basically.
Yes, technical condition.
Okay,
yes.
okay. At least you have local existence of this conformal heat flow, and that's already something, yes. But maybe even for weaker initial condition, one could actually establish local existence.
Yes, right.
Yeah. Okay, that was my main question. Are there other questions or comments maybe?
I have a question.
Yes.
About the simplest case, about harmonic maps. You mentioned Chang-Ding result about the existence of the blow-up.
Yes.
And this is, if I remember, maybe you will correct me, this result is obtained for rotationally symmetric case, yes?
Correct, yes.
So now, if you start with sufficiently big initial energy, but otherwise you have arbitrary general case, is there any result about the existence of blow-up, or is it open?
I have a result from topping. But it's not mapped to S2. I'm not 100% sure, but it's mapped to S2 times S1 or something. And under some very precisely defined metric on there. But yes, there. No, it's still rotationally symmetric. Yeah, so far I know 2 counterexamples, but both are rotationally symmetric. But maybe you're right, there could be open question.
Okay.
Yeah.
Okay. Thanks.
Thank you for the comments, Ben and remark. Are there any questions by the audience?
I think Yoshikazu has a question.
I don't see his raise. He raises his hand. No.
Maybe no.
Julie just wrote that's a very nice talk. Okay.
Okay.
That was a comment. Thanks, Julie. Okay, if there are no any more comments, yes, the talk was really very beautiful. Thank you. So everyone received actually a reminder email to this talk sent automatically by Zoom. And when you go in this email at the very bottom, you will find the link to the coffee break, which we have now. So please, I will now close this webinar. And then if you are interested to have some question to Weibo, please join us in the coffee break now after this seminar. Okay, then thank you everybody and see you. Bye.
Bye.
Thank you. Bye.